Okay, hello and welcome to the Radical STEM Homework Help Livestream. So, you can bring your math and science questions, put them in the chat here, and we will do our best to help you solve them live. In the meantime, I'm just going to be solving some math problems to pass the time. Today I'm actually going to be working on some homework for my advanced differential equations class, so that's fun. But just like the message on the whiteboard says, don't hesitate to interrupt, because we are here to help you first. Okay. So we're going to start with this one. It's actually modeling a circuit with differential equations. Point A here, or node A. We've got current I1 there, I2 going that way, and I3 going that way. So we are given I1 equals I2 plus I3. All of the current going into node A has to equal all of the current going out of node A. And we're also given I1 dot, I guess we'll use dot notation since these are time derivatives, is equal to negative 12I1 plus 12I2, and we get I2 dot is equal to negative 3I1. So the first thing we need to do is write the system in matrix form. So write as, I'm going to put that up a little higher since we have more room. I, the vector prime, equals A, the matrix, times I, the vector, where I, the vector, equals I1. Oh, okay, we'll write it sideways. I1, I2. Okay, so to do that, we basically are going to just adapt these coefficients and write a matrix. So we have an I1 prime. I guess I will do prime since the vector notation it gave us uses prime. We have a coefficient for I1 and a coefficient for I2. In I2 prime we have a coefficient for I1 but nothing for I2. So we'll say that that's 0 I2. And then if we take these, we would have, if we stack them up in a vector, we would have I prime over here. So exactly the vector that, or the derivative of this rather, is I1 prime, I2 prime. And that's going to be equal to negative 12, negative 3, 12, 0, I1, I2. So here we have I prime, the vector. We have the matrix A, and we have I, the vector. So there is, as it wanted, I prime equals A times I. Okay, what's next? Find e to the TA. Okay. I'm going to rewrite A up here. Now, if you're not in the advanced differential equations class, this might take some explaining for what that actually means, because the way we've written this, we're raising e to the power of a matrix, and what would that even mean? It's actually defined as basically just the way we would define e to anything else. We have the sum from 0 to infinity of x to the k over k factorial. And similarly, this is defined as the sum from k 0 to infinity t times a to the k over k factorial. So you can even break that up and say that it's the sum of t to the k over k factorial times a to the k. So if you have a matrix where it's really easy to compute certain powers of it, or you have a matrix which after you reach a certain power it all becomes 0, then you can have a really easy finite sum of matrices to compute this directly. I don't think this is going to be one of those matrices. So we're probably going to have to find its eigenvalues, and then based on that there are a few formulas we can use to compute e to the TA. So first find eigenvalues. So to find the eigenvalues, start the way we always do. We said 0 equal to the determinant of a minus lambda I. So that is 0 being equal to negative 12 minus lambda times negative lambda minus negative 3 times 12 . So 0 being equal to, we always get our positive lambda squared. here we'll get a positive 12 lambda. That's it for this piece. Then we'll have a positive 3 times 12 is 36. So what multiplies to 36 and adds to 12? That would be 2 sixes. So this should be 0 equal to lambda plus 6 but squared. Yeah, because you would get a 6 lambda and a 6 lambda, which would add to 12, and you would get 6 times 6 being 36. So that means lambda equals negative 6, and we have repeated eigenvalues. Okay, and let's see what our formula is for that one. Okay, so for repeated eigenvalues, we have e to the ta is equal to e to the lambda t times I times the quantity I plus t times another quantity a minus lambda I. Yes, that's it. And we can see this is a bunch of scalars multiplying matrices and then matrices adding together. So this will give us a matrix value at the end of it. It won't turn into a vector or a scalar or anything. So first, let's get a minus lambda I. So we're going to have basically one matrix multiplication. So actually I think I'm going to go ahead and try to write those two matrices on the next line, and then we'll try to multiply them after that. So e to the negative 6t times I means we'll get e to the negative 6t on the diagonal, and zeros elsewhere. Now for this whole matrix, we have the identity matrix plus this other piece, which means that on the diagonal we're going to have a 1 plus some other stuff, and then we would have zeros in these spots, but we'll most likely have stuff to add from this matrix. So a minus negative 6i would be adding 6 to our diagonal. So that would be a negative 6 here and a positive 6 there. And then we're multiplying it with t. So this will be negative 6t, 12t, negative 3t, and 6t. Okay, that wasn't so bad. I made it a lot harder than that when I did one of these problems on one of my other homework problems earlier today. Okay, so now I'm not sure why exactly I wrote this out as I did, because we can make this a lot easier if we don't try to do this matrix multiplication. This is still e to the negative 6t times I. Any matrix times the identity matrix is itself, which means that we can basically just get rid of that I, and then we have a scalar multiple on this matrix. So we're finally going to have that e to the ta is e to the negative 6t times 1 minus 6t, negative 3t times e to the negative 6t, 12t times e to the negative 6t, and 1 plus 6t times e to the negative 6t. I don't know why I put that coefficient at the back instead of the front. Anyway, so there is part B of the problem. What's next? Solve the initial value problem consisting of this system with the initial conditions that I1 of 0 is negative 4 and I2 of 0 is 0. Okay. So we'll leave that right where it is. We'll erase everything else up here. Do we need A written down anymore? I don't think so. If we do need it, it's easy enough to see it off of our original system. Okay. So we have the initial condition I of 0, the vector, is equal to negative 4, 0. Now what's useful about this matrix e to the ta is when you are solving a system like this, any system x prime equals ax with an initial condition x0, or whenever your system starts, then a solution to that system is e to the ta times x0. So what we can do is take this initial condition, multiply e to the ta on the right by that initial condition, and then we'll get a solution to this system. So this tells us that the solution to our system I prime equals ai I being equal to e to the ta times negative 4, 0. And when we do this vector multiplication, we're going to take negative 4 of the first column and 0 of the other column. So this is going to be a 2 by 1 vector, and it's going to be, we'll say, 4 times 6t minus 1 e to the negative 6t, and 12t e to the negative 6t. So, starting at t equals 0, this will model the currents I1 and I2 for this circuit, where I1 is given by 4 times 6t minus 1 times e to the negative 6t, and I2 is given by 12t e to the negative 6t. And we can see with these both having a negative exponential term, both of these are eventually going to approach 0. Because of primarily probably the resistor. That's the big one that's going to dissipate energy from this system and make the currents decrease over time. But I believe an inductor like this also has some resistance-like quality. It's not exactly resistance. Okay, what is next? Graph the three currents I1, 2, and 3 for t between 0 and 2. What is the maximum value of I2? Okay. I don't know if I want to graph those right now, just because we don't have a lot of space, but we will find the maximum value of I2, and I will make that graph later when I turn in my assignment. Okay. So if, write it up here, I2 equals 12t e to the negative 6t, find max value on 0 to infinity. So this is now a calculus 1 problem. So to find the maximum, we take the derivative and set it equal to 0. Find our critical points. So 0 equals the derivative of this. We have a product rule going on. So first we'll take the derivative of t and leave everything else alone. Then we'll, on the other term, take the derivative of e to the negative 6t and leave the rest alone. So we'll get an easy 12 e to the negative 6t. Then we'll get, go ahead and write plus 12t negative 6 e to the negative 6t. 12 times 6, that's 6 times 6 times 2, which is 36 times 2, which is 72. So this is 72t e to the negative 6t. We have an, oh, you know what? I'm not going to do that. Hold on. Also, I dropped that negative 12 times 6. We have a 12 e to the negative 6t in both terms. So divide the whole thing by 12 e to the negative 6t. And we'll get 0 being equal to 1 minus 6t. Much easier to deal with. And then that's the same as saying 6t is equal to 1. So t is equal to 1/6 suppose this is all in SI units, so it reaches its maximum value at 1/6 of a second. So I2 of 1/6 equals 12 over 6 e to the negative 6 divided by 6. So that's e to the negative 1. So that's 12 over 6 over e. 12 over 6 is 2 over e. So that's about 2 over 2.7. Which is, I'm getting real approximate now. That's close to 2/3. Let's see what the exact value is with our calculator. Or, you know, as many decimal places as it's able to give us. 0.735. So, yeah, that is very, very approximate. Okay, that was fun. Let's see what we have next. Okay. So this one gives us a 3x3 matrix to work with. So we're given a matrix A, 3, negative 1, 0, negative 2, 3, negative 1, 0, negative 2, 3. And then we have eigen value vector pairs given for us. So lambda 1 is 1, v1 is, I'm going to write these sideways to save space, 2, 2, 1. Lambda 2 is 5, v2 is negative 2, negative 2, no, negative 2, positive 2, negative 1. Lambda 3 is 3, v3 is 2, 0, negative 1. And we're also given an extra equality that seems a little random. See if I can fit it up here. this is what we're given. We have the 3 eigenvalue and vector pairs for this matrix, and we have the inverse of some constant matrix. And what it wants us to do is find e to the ta. And we could do this the hard way. We could, you know, use our series definition, e to the ta being equal to the sum of t to the k over k factorial a to the k. And certainly if we were entering this in like a computer system, we could just brute force compute that up to however many terms we want. Our formulas that we were using before, where we had e to the ta is e to the lambda t I plus t a minus lambda I. Well, for one thing, that was only for a matrix with repeated eigenvalues, but also I'm pretty sure this is also only for 2x2 matrices. So we're actually going to use a different way of solving this, or of computing e to the ta, using something called fundamental matrices. So a fundamental matrix corresponds to a system. So where you have a system of differential equations, x prime equals ax, I'm going to shorten that, fund matrix, has a fundamental matrix Z where it is composed of the eigenvectors. So there can be infinitely many fundamental matrices as long as each column is an eigenvector of A. Then Z will be a fundamental matrix. Also, all of those eigenvectors have to be linearly independent. So you couldn't have like 2, 2, 1, 4, 4, 2, and 8, 8, 4 as your 3 columns. They have to be linearly independent eigenvectors. And what we can do with this Z matrix, where oh wait, no, I said that wrong. These shouldn't be eigenvectors, these should be solutions to the system. So where x1, x2, x3 are linearly independent solutions of x prime equals ax. So the columns of Z are made up of these vector solutions for the system, which are based on these eigenvectors. It's e to the lambda t times the vector. So it's not exactly the eigenvector, it still has to be a function of t, because now I'm going to go ahead and erase all of that. here's our theorem that we're going to use. E to the ta is equal to z of t times z of 0 inverse. So if we have a fundamental matrix for x prime equals ax, then we can multiply that fundamental matrix by the inverse of it when 0 is plugged in to all of those e to the lambda t's. And as luck would have it, this is actually z to the 0. So our fundamental matrix would be z of t equal to, we would have e to the 1 times t, so e to the t times 2 e to the t, 1 e to the t. Here we would have negative 2 e to the 5t, 2 e to the 5t, negative e to the 5t. Then we would have 2 times e to the 3t, 0, and negative e to the 3t. So this is our fundamental matrix that we're going to use. And if we plug in 0 for all of these e to the something t's, z of 0 becomes e to the 0 is just 1, anything to the 0 power is 1, so we just get 2, 2, 1, negative 2, 2, negative 1, 2, 0, 1. And I dropped a negative. That is exactly the matrix that it gave us at the beginning of the problem. And it tells us the inverse of this matrix is that one. So z0 inverse is that. So if we multiply this matrix by that matrix, we will have found e to the ta. Now the only thing standing between us and that is is doing 3 by 3 matrix multiplication by hand. Okay, I'm gonna have to erase some stuff. Let's start this up here. 2e to the t, 2e to the t, e to the t, negative 2e to the 5t, 2e to the 5t, negative e to the 5t, 2e to the 3t, 0, negative e to the 3t. This is going to look a little sloppy. We'll say e to the ta is equal to z of t times z0 inverse. So this is z of t. This is z0 inverse. Okay, now comes the fun part. Let's get our dot products going. So we're going to take the dot product of this column with that row. So we get 2 times 1/8 is 1/4 e to the t, negative a half e to the 5t, a half e to the 3t, all for the very first component. Oh, this is going to be huge. I don't even know if I can write it all on this board, because every term in this matrix, every one of these 9 matrix entries is going to be a sum of 3 different exponential functions. Oh boy. Well, here's something we can do. Maybe we'll be able to fit it if we just kind of condense some things. So if we factor out 1/4 from this, we would have a lot more ones, and we could just write a 1/4 out to the side of our matrix multiplication. These would become 1/2. That would become a 2. -2. And once we do this, that matrix will no longer be exactly z0 inverse. I guess I could have just redrawn the bracket. All of this together still makes z0 inverse. Okay. I'm going to make liberal use of parentheses here, and maybe we can fit it all. So the very first entry, we would have e to the t positive e to the 5t and 2 e to the 3t. Okay. So for this one, we want to dot this column with this row, I believe. Right? Even though we've done a lot of matrices work in this class, I haven't multiplied a big 3x3 matrix by hand in a while. Let me check. We take first column times the top row for the first entry. Next entry we take, yeah, first column times the second row. Okay, I had it right. I just didn't trust myself. So that gives us e to the t minus e to the 5t and 0. 0 because of this, not because of that. Yeah, 1 times 0 is 0. So next we'll dot this column with the bottom row. So we'll get a half e to the t plus a half e to the 5t and negative e to the 3t. Okay, now we're working with this column. So we'll get 2e to the t minus 2e to the 5t plus 0. Then we'll get 2e to the t plus 2e to the 5t plus 0. And we'll get e to the t minus e to the 5t plus 0. I like that row because it has, or that column, because it has a bunch of zeros. Now we'll use this column, so we'll get 2e to the t positive 2e to the 5t negative 4e to the 3t. Then we'll get 2e to the t minus 2e to the 5t plus 0. And finally we'll have e to the t plus e to the 5t plus 2e to the 3t. And there it is. Oh, all times 1/4. What a doozy of a matrix that is. I'm going to reposition that equal sign. E to the ta equals. Okay, well, that's fun. I'll get to come back later and rewatch this video to copy down my answers to turn them in. Okay. So we've got about 10 minutes left in the stream. I think instead of doing more large tedious problems like this, maybe we'll find a nice relaxing integral to cruise out on. Okay. We're gonna have integral of 4x minus 2 over x cubed minus x dx. So first thing I'm seeing is, let's factor the denominator, x times x squared minus 1, 4x minus 2 dx. And let's also break this up at the subtraction there in the middle. So we're going to have two integrals. We're going to have 4 times the integral of x squared minus 1 on the bottom with x on top. I'll put the 4 back inside just so it's easier to see what we're doing. Dx minus the integral of 2 over x times x squared minus 1 dx. So here we get the really nice cancellation. Here we don't. So I think I'm seeing partial fraction decomposition happening, especially for this one. So this is going to be PFD. What about this piece? The integral of 1 over x squared minus 1. If it was x squared plus 1, we would have the very easy tangent inverse antiderivative. Maybe that one will be partial fractions as well. Okay. Can we factor x squared minus 1? No. Yeah, it's not this squared, it's just a thing squared inside of there. So, with partial fractions, we're going to say, let's do this one first. 1 over x squared minus 1 is going to be equal to ax plus b over, oh wait, we can't do a partial fraction of, I think we just need to do the partial fraction on the original integral rather than trying to break it up. So, PFD, 4x minus 2 over x times x squared minus 1 is going to be equal to some number a over x and some bx plus c over x squared minus 1. Oh man. Will this really help us though? Because then we'll still end up with an integral of something over x squared minus 1. I don't know. We'll never solve it if we don't try. We might never solve it anyway. So do our normal trick, multiply by this denominator, so you get a attached to x squared minus 1 and bx plus c attached to x. Then we'll plug in some choice x values. So let's of course try x being equal to 0. Get negative 2 equals negative a, and that's it. So a equals 2. Okay. Try the classic x equals 1. Get 2 on this side. That becomes 0. We get b plus c. Okay. And what else could we do? Negative 1. Another classic. Negative 4 minus 2 is negative 6. That again becomes 0. We get negative b times another negative is positive b, and then negative c. So let's add those two. We'll get negative 4 equals 2b, or b equals negative 2. Get that, and then that means that negative 2 plus c, add the negative 2, c is 0. Okay. Wait, that doesn't make any sense. How could c be 0? Because then we would have negative, no, hold on. You add 2, c would be 4. Duh. Okay. Does that make sense? 4 minus 2 is 2. Negative 2 minus 4 is negative 6. That works. Okay. So our integral is now going to be 2 over x plus negative 2x plus 4 over x squared minus 1 dx. And look at that, we are not in any better shape, because yeah, if we can integrate that part. We could split this up at the addition, and we could probably handle negative 2x over x squared minus 1. But then we would come back to integrating 1 over x squared minus 1. So, yeah. We tried. Didn't get there this time. But that is time for us to end the stream. So if you've been out there watching, thank you for watching. Hopefully next time you'll have some homework problems, because it's always more fun to help you guys with yours. Alright. And until next time, have a radical day.